Hello, hello, hello. Welcome everyone to the fifth stream in the Microsoft AI Chat App Hack series. I'm Pamela. I'm from the Python Cloud Advocacy team, and I work a lot on AI chat apps. And today we have a special guest from the AI search team. You want to introduce yourself?
Hi, folks. My name is Matt. I'm a program manager on the AI search team, and today I'm here to talk to you about how we combine GPT-4 vision with our sample.
Yes, awesome. This is gonna be so cool. I gotta say, it's just really cool to see what you can do with images and vision and how really capable these models are. So for those of you who don't know, we're running this AI chat app hack from January 29th to February 12th. And the goal of this hack is to really share a lot of information and knowledge about how to build RAG chat applications. So these are chat applications that are combining your data with the inference power of a large language model, like GPT-3.5 and GPT-4. And we're trying to cover all the different sorts of technologies and approaches that you might use when you're developing these sorts of applications. So this is our fifth session. So we've already covered a lot of things, and we've got a bunch more things coming up next week. So we hope that you watch the previous videos, join us for the next videos, and we hope to see you joining the hackathon and submitting a project so that we can see what cool applications you make. And I hope you get some ideas today from Matt's presentation. So let's go over to Matt now and learn about vision.
Thank you so much, Pamela. So today we're going to be covering a couple topics. I really wanted to start with, if you have not seen it, I would really encourage you guys to check out the Azure Search OpenAI demo repository. It's kind of got everything you need to get started with combining Azure OpenAI with Azure AI Search. So I'm going to be talking about a very specific feature, which involves using GPT-4 Turbo with Vision combined with our repository. What does that actually mean? So I've gone ahead. I've set up the sample. It's actually running locally on my machine. So what this means is that if I go into this little developer settings tab here, I'm seeing a lot more additional options than I was before, in case you guys have deployed it previously. There's this little checkbox that says use GPT-4 Turbo with Vision. If I uncheck it, I lose a bunch of options. You notice the examples change, but I check it, I get a bunch of new options. I can now search images for my index. And in addition to my retrieval mode, I've got some more customization. So I'm going to issue a query. And unfortunately, it takes a while to get an answer, but I've pre-run this so we can kind of see what the output might look like. So I've asked the model, hey, go to the search index and compare the impact of interest rates and GDP in financial markets. What do we have in the index? Well, we have a bunch of text, which is actually taken out of the image itself, and we actually have images. The real cool thing about GPT-4 Turbo with Vision is that it can actually combine these two sources of information. So I'm not just looking at the text itself. I see there's a graph. I can actually look at that graph and make decisions based on that. And we can kind of see in the thought process, we can see like, hey, we're passing a certain prompt to this image. There's a lot of kind of hard to parse things in here. We'll get into a little bit more depth into how this actually works later. But what's important is I give it this text prompt. It goes to my search index, and it actually uses both images and text to create this answer. And it's actually citing specific images as the source for its answer. So we're kind of going beyond just like a simple text search. And it looks like the search just kind of finished. What's super interesting is I asked it, can you identify any correlation between oil prices and stock market trends? It actually picked up on this table saying, hey, look, there is a correlation. So it actually was looking at the image. There's no text in the supporting content here. It's literally just an image, which is pretty cool. So you might be wondering kind of how does this actually work? And to kind of dive into that, I actually wanted to start with a little bit of a simpler sample. In the kind of notes for today's talk, I have a link to a repository I've created called AI Chat App Hack Vision. This is a much more cut down version of our sample, and I'm really specifically only focusing on how to do image search, because getting image search working is a key part of this sample. So if we look at the cut down sample a little bit, it's really simple. It's just an empty search box, and I've preloaded some pictures if you've ever used Vision Studio before, they have a bunch of sample data sets, and I use the one called nature. So if I type in a text prompt, notice there's no images here. I just search for the text beach. I get pictures that look like beaches back. I type in mountain. I get pictures that look like mountains back. So to start off with, we're just going to understand, given a text query, how can I actually retrieve images that kind of look like the text, which is kind of interesting because there's no annotations at all on these images. It's purely just a picture of a mountain, but I want to be able to take this text and actually go to the images. So when we clone the repo, you can kind of open it in VS Code. There's a bunch of folders here. We've got the app folder, which is kind of like the front end and the back end. Custom skill, we're going to talk about that a bit later. Infra for kind of standing up all these things. Notebooks, we're going to dive into that a little bit later when we talk about specifics of how these things work. And scripts for setup. So when I talk about setting up a search index, basically the service we're using under the hood, it's called Azure AI Search. And if I look at the docs for this, where did we go here? Search as a service. So basically, if you have an Azure subscription, you can provision this. You can create search indexes and fill them with documents. How do I actually do that, right? What's the actual steps that I need to do to get images into a search index? Because typically when you talk about search indexes, you talk about just searching plain text content. The details about that, there's a specific file in the scripts directory called setup search service. We're using the Python SDK here, so we don't need to kind of mess with calling REST APIs ourselves. We're actually using a complete kind of much easier to use SDK, so you don't need to kind of mess with calling REST APIs yourself. So when we talk about searching images, what we don't do is we don't actually upload the images themselves to the search index. Images can get really big. It's kind of confusing to reason about images, just like if you have a JPEG, for example, if I actually look at these files, they're JPEGs. They're not, or these are PNGs, but there's, I think there's some JPEGs in here. These PNGs and these JPEGs, these are bigger files. They are kind of big. Like it would be too hard to just kind of give in a JPEG and giving a text. Like there's not really an algorithm I can think of in my head to say, hey, you know, match the picture mountain with something that looks like a mountain. Instead, we're actually going to lean on something called the image retrieval APIs from Cognitive Services. So if I go to vectorize, here we go. There's actually an API that we can use from Cognitive Services that has to do with something called vectorizing images. So if you've never heard of this before, what vectorizing images means is we're going to take this JPEG, this PNG, whatever, and we're going to turn it into an array of numbers. We can actually store this array of numbers very efficiently in the search index. And the kind of Python syntax for doing this is search field data type.collection of single. What that means is that we've now basically, you can think of it almost as compression. We're taking a picture, it could be of anything, and we're smushing it down into an array of just about 1,000 numbers. And these numbers, it's kind of terse. It's hard to interpret. So if I were to go to my search index and I set this up, so if I go to the image embeddings index, so I've already indexed this ahead of time, and I just click search, I'm going to see there's all these crazy numbers in here. -1, -4, 0, 1. It's kind of hard to understand. But what these numbers mean is very interesting. These numbers are kind of that Cognitive Services API we called. We give it an image, and it's basically saying my understanding of what this image is now being compressed into 1,024 numbers. And maybe a human can understand what it means, but computers can. There's specifically a model that generates these things called embeddings. These embeddings are interpretable by the model. The Cognitive Services API also has another kind of parallel call called vectorized text. And what that does is it takes something like the word mountain and it turns it into exactly the same dimension array. So it's another 1,024 dimension array. And by comparing these two arrays together, we can get a sense of, hey, this text is much more similar to the picture. So when I type mountain, what I'm doing is I'm saying, hey, turn it into this array of numbers, and then compare it to all the other array of numbers in the index, the ones that are the most similar, well, because they're similar, that means that they're supposed to be related. So when I type like sand, I vectorize it into this array, I get something that looks similar to these arrays, even though these are images, they're completely different than text. So we use a couple of features in Azure AI Search to do this efficiently. The first thing we do is we need to actually build a search index that's really efficient at searching these large arrays of numbers. A normal search index, typically how it works is it uses something called BM25. And you can kind of think in your head, it's like, well, I'm taking words and I'm breaking them into little bits, and I'm trying to like really efficiently search those little bits of words. And that works really well for just plain text. The problem that we have now is that we have an array of numbers, and that's not really a good fit for the traditional search paradigm. What we do instead is we have to define something called a vector search algorithm. And this vector search algorithm kind of says, okay, I need to build a new type of index. In this case, we use the index type called HNSW. HNSW stands for Hierarchical Navigable Small Worlds. And think of it as basically taking these large arrays of numbers, like many of these, and making it so we can really efficiently search through them and find ones that look similar to the array I'm inputting. So for example, if I vectorize the text mountain, I have this input array, and I basically say, hey, find me all the vectors that look similar to this one from the index, and HNSW can do that really quickly. The next thing we need to do is we need to find something called a custom vectorizer. And I've actually pulled up the doc page for this here. A vectorizer is basically something that makes it super easy, given a text query, to turn it into this array. And if I don't have this, I can still do it, but I have to do it myself, and that's kind of harder to do. So by using this vectorizer feature, I'm able to just really kind of simply send in a text query like mountain and let the search service deal with actually turning it into this array so it can actually search the index. So once I've created the search index, I actually need to figure out where am I getting my data from. There's a feature of Azure Search called indexers. And this feature, basically what it does is it allows you to take a bunch of source data. In my case, I've got this huge amount of pictures. I've got over 200 pictures here. And I can basically use indexers to automatically turn these into embeddings, which I can put in my search index. And I don't have to worry about orchestrating that myself. So I want to use the built-in orchestration to Azure AI Search. The first thing I do is I create a blob data source. So I've got a helper function that kind of sets up a connection to Azure Storage. In this script, I actually have a Python code that makes sure a container in Azure Storage is created, takes all the pictures in the sample directory and uploads them. So by creating this data source object on AI Search, I'm creating a connection and I'm saying, hey, when I run my indexer, go to that container I uploaded when you're trying to find data. Now, the next thing I need to do is I actually need to figure out, okay, I've got a container full of images. How do I actually turn those into these arrays, these embeddings? There's another piece of functionality in AI Search called a skill set. And what this does is it kind of says, okay, given a bunch of source documents, I want to run some AI-related operations on them to get some structured output. So when I define a skill set, I'm basically saying, hey, when you run this indexer, you need to actually run these AI operations on the data before you put it in the index so that we're putting the right things in. Azure AI Search does a bunch of stuff for you for convenience. It basically says, hey, you're extracting a bunch of images. I'm going to give you the URL to that image. Blob containers. In this case, we're using a public blob container, but we have the ability to generate what's called SAS tokens. Think of it as like a way to temporarily give your skill set access to these images. And we're basically defining something called a skill. This skill is just kind of a wrapper around an Azure function that actually does the work of vectorization. So when we define a skill set, we can create all these little skills, which are wrappers around different functionality, and we can chain them together by using inputs and outputs so that, for example, in this case, there's only one skill in the skill set. It's very simple. It takes this blob URL and a SAS token from the blob container, and it transforms it into this vector array embedding, whatever you want to call it. And then we're going to take that output, and we're going to eventually put it in a search index.
Matt, we have a couple interesting questions.
For sure.
So just to clarify, with the vectorizer, your vectorizer is using that computer vision multimodal embedding model, right?
That's correct.
Okay. And then someone was wondering, like, you're doing this with photos right now. Would this work with things like technical drawings, like CAD plans, that sort of thing? Like, what sort of images does that multimodal, model work well for?
That's a great question. So the cognitive services. So in general, these models work really well when they're the image you're trying to embed. It's been trained on. So I don't exactly know what makes up the training sets of the cognitive services model, but I can tell you it's been trained on like receipts, business documents, photos of nature. This data set is just a sample data set I downloaded, but I would imagine this is kind of a thing you have to try out. So if you had a technical drawing, what you can do is you can just try calling the API on it, and you can try vectorizing some text and seeing how well it compares. The key is really what these models were trained on. If you give it an image that it hasn't seen before, it doesn't know what to do, so it won't generate a representative vector. So the name of the game here is either finding a model that matches your data set pretty well. These cognitive services models are very generic. They've been trained on a lot of images. Chances are, unless you're trying to do something really specialized, it's probably seen images that you're trying to vectorize.
Yeah, when OneNote, there is a note in the docs that says do not use it for medical diagnosis. So just want to put that out there specifically. There's also questions. So are you using, when you're indexing both text and images, are you making two indexes? Or are you making a single index? Like, what's the general approach there?
That's a great question. So Azure AI Search has the ability to have multiple fields in the same index. So I could literally just add, so in this case, I've got a URL field, which is a string. If I wanted to vectorize text, I would just copy paste the definition as vector fields and call something like vector text. You can have multiple vectors in the same index. And when you search, you can use a feature called multi-field vector search, which is what this sample does. So if I go back to the main sample and I issue a search, you're going to see I have this retrieval mode, and you have this vector fields multi-query vector search. When I issue this search, can you identify any correlation between oil prices and stock market trends? Depending on which option I pick, it changes the field it's searching on. So I've picked text and image embeddings, which means it searches both the text vector and the image vector that I've set up in my index. So the answer is you can use either one or the other or both.
Okay, but yeah, so it is a single index. We don't need to make two indexes. We can just use the same index in multiple fields. And if it's got a text embedding, great. If it's got an image embedding, great.
Yeah.
Cool. Okay, I think we're good on questions.
Awesome. Okay. So basically, like, to kind of build off that question, imagine that you can have different outputs. Actually, going back to the skill set definition, you could have multiple outputs from a skill. So instead of having a single output called vector, in my case, I'm just only vectorizing the image. I could have two outputs. I could have like a text vector output. So that's kind of how the skill works. So I'm going to jump over really quick. So these skills, typically how they're implemented is they're implemented through Azure Functions. So I literally have checked in this repo, I've checked in a folder called custom skill. This is using the V2 Python interface. So there's a file called functionapp.py, which is like the main source code of the function. It's pretty simple. There's some extra code in here that covers this skill. This skill is playing a double role. I talked about vectorizers earlier. So this skill is actually behaving both as a custom vectorizer. So when I issue a search, I can vectorize that text. And it's also playing a double role as the custom skill for ingesting these pictures into embeddings. So this is just a bunch of code. There's a specific contract custom skills follow. You can copy paste this code if you want to use skill sets yourself, because the contract, in my opinion, is the less interesting part. What's more interesting is the fact that inside this custom skill, all I do is I call the vectorized image API. And I basically say, hey, I could have many images being sent to me. I literally just call this API. and I pass back the vector results. So I'm in my custom skill, I'm not even worrying about loading any models. I just kind of call the Cognitive Services API with the input image. I do have code to call it vectorized text, but I'm not actually storing that in the index. This is only being used when I'm actually issuing searches. So I'm going to go back to the setup code. So finally, I kind of create this indexer object, which ties everything together. It takes that skill set I defined. It takes the target index where I'm supposed to put the data in. It takes a data source, and I actually go and I run it. And what I can do in Azure AI Search is I can actually go in the portal. I have a bunch of indexers, but if I look at my image embedding indexer, I have this concept of like execution history. So I can kind of monitor like, I had a bunch of problems setting this up. So you can see I've got history of failure. I can kind of go in and I can like look at errors. So if I had a problem, like in my case, when I originally created my, the sample, I couldn't get the custom skill to work. I had to debug it. I can actually see a record of that error. So if you're setting up a custom skill, hey, I'm having some problems, I can use the execution history of the indexer to investigate those errors. Finally, I actually had a successful run. I successfully ran through all 260 images. So by preserving the record, it's very useful for debugging. So in addition to any logging you set up on the function, the indexer itself offers some investigating capabilities. And finally, when I go to my index, because I set up this custom vectorizer, I can actually just put the text that I want to search here. And I don't get as nice of a preview as I did in my actual demo app. The demo app understands how to display images, but if I just like want to use the portal to investigate, I can actually see that I'm actually, if I drop under the hood to the JSON view, the portal is all it's doing is it's calling the search API, but it's using this special object called vector queries. Because I defined a custom vectorizer on my index, I can actually just pass this text directly to the search service, and it calls the custom vectorizer, gets the vector back, and then it does the search. So this is pretty convenient, and this is very useful if you just want to use the Search Explorer feature to just kind of test your search results. You don't need to build an app. You can just kind of see if your search results make sense. Of course, the downside is you're kind of looking at a very JSON-oriented view. Using the sample to kind of stand up and do image search, you'll actually be able to see a preview. So that kind of covers the standing up the sample. So let's go back here. So there's a couple of differences in how the sample ingests images versus how the demo actually does it. And I want to cover two key aspects of that. So the sample is just purely searching images. It's not changing the images in any way. So we ran into a very interesting problem in this demo. We wanted to support citations. And out of the box, GPT-4 Turbo with Vision provides no way to kind of determine, like, I give it a bunch of images. So for example, if I go to my thought process, you can kind of look at the prompt here. The prompt just uses this feature where it basically puts the data in as this kind of base64 encoding. But there's no way once you give GPT-4 Turbo multiple images to know what image did it use to answer the question. So we did something very clever. What we did was we actually, when we do ingestion in the demo, we actually go ahead, we load up the PNG and we write the text source file name : and then the blob name in it. So you can actually see this in the demo. So this is not something we do for convenience. This is the actual picture itself. We've modified it to write this text on the top. And if we look at the thought process, we can actually see the kind of prompt. And I actually might want to copy paste this into VS Code so we can see it a bit better. And I can't do it. Okay, so you're an intelligent assistant. The documents contain text, and we actually tell it each image source has the file name in the top left corner of the image with the coordinates 1010 is in the format source file name file name. So in the prompt, we actually tell it, by the way, this source image, it's going to have its citation in the top, and format your output so that we can actually get this image back so we can actually display it. So we kind of use prompt engineering to generate citations. So the code to do this, to actually draw, we just use a library. We use PyPDF and we use Python image library. We just kind of draw the text before we upload the image. So this is a really important step to do if you do want citations in whatever app you're building, because it's really hard otherwise, because GPT-4V will just give you an answer without telling you what image it's from. So that's kind of a key difference that the demo does that this sample app does not. So now that we covered that, I wanted to kind of switch gears a bit, and I wanted to kind of dive a bit into more about how these image embeddings actually work. Like kind of how do these models, how are they able to kind of combine and switch between text and images? So in my sample that I've shared today, I've got a notebooks folder. There's 2 notebooks in here. There's one called Clip, and there's one called GPT-4 Vision. So we're going to start with Clip. So this is now a long time ago. This is January 5th, 2021. This was one of the kind of first big models that was really popular, which what it did a very interesting thing. The way it was trained, they combined something that can encode text into these embeddings. They combined something that could encode images into the embeddings. And they basically made it so that these embeddings ended up being in what they call the same space, so they could be directly compared. So the way these models are built, and there's a link to this article if you want to read it in the repo. The way these models are built, they're trained together with both text and images. And because they're trained together, they actually are able to kind of make this comparison between text and images. So not using the Cognitive Services API anymore, you can just kind of go on Hugging Face and you can download this model. There's a bunch of variants of Clip. I'm just using the base patch 32 one. Which model you use, I think it depends on the scenario. This is just kind of a good default choice. So when I look at this notebook, Clip can do a lot of things. And we are using the image similarity use case. This is an interesting use case where we're basically saying, I want to generate a label. I want to see if these labels describe this picture very well. So in this case, I passed in 2 labels, a photo of a mountain and a photo of a beach. And I load up this image, and the images don't really have good names. We're going to see how we're going to fix that later on. But I load up this picture 33, and I want to say, does the label a photo of a mountain or a photo of a beach match it better? So when I use Clip, I can kind of say that given a probability between 0 and 1, does this label describe this image very well? And Clip out of the box says, oh yeah, this is not a photo of a beach. You'll notice the probability is near 0. Clip really doesn't like combining the text, the photo of a beach, with this image. But what I can do is I can actually combine the text, a photo of a mountain, with this image, and Clip's like, yeah, this makes a lot of sense. So using these models, you can do a lot with these models just beyond search. This is just one example. But I also want to know, how do I actually get embeddings out of this model that I can actually use for search? So there's just a really simple property, image embeds and text embeds. And you're going to notice this uses a library called PyTorch. This torch.size is just a data type from that library. Basically, the way to interpret this output is, hey, there was one image, so the dimension is basically saying 1 row, and there's 512 kind of columns. So that means that if you remember earlier, the Cognitive Services one had a dimension of 1024. This means that the dimension of the Clip output is 512. Likewise with text embeddings, because I passed in 2 labels, I get 2 rows, and they're each 512 dimensions. And so the general way you compare these, how do I actually take these embeddings and do something useful with them? The general way that people do that most of the time is they use a technique called cosine similarity, which basically means they find the angle between these 2 kind of massive 512 dimension arrays. And the angle between these embeddings, it ends up being meaningful because the model, basically the model's job is to take these images, take these text things, and basically put them in some kind of geometric space. That's like, and basically the angle between these objects in geometric space has meaning. If the cosine similarity is closer to 1, that means that, hey, I think these concepts are related. If the cosine, the lower it goes, the model is basically saying, I think these concepts aren't really related. And in this case, CLIP thinks that cat and dog are much more related than the concepts of dog and lion. You can see that there's nearly basically a 10% increase in relevance here. So that's kind of how the very low level introduction to how you actually use these image embeddings and text embeddings. You can do the same exact thing with images, just there's some source code where we have basically picture 33, 34, 35. I'm only looking at the image embeddings this time, and I'm basically just saying, hey, what pictures are similar? So if we look at these pictures, picture 33 is the mountain and the sunset. 34 also has a mountain, but it's not sunset. There's a forest. Picture 35. CLIP thinks that 34 and 35 are more similar than 33 and 35, right? Which makes sense because in picture 33, there's no forest, but in picture 34, there is. So it's very good at kind of like visually, like, I can't put it necessarily into words, but by using cosine similarity, it's a really easy way of kind of taking these big arrays and kind of making sense out of them. The next notebook I wanted to show you guys had to do with actually using GPT-4 Vision itself. So when I talk about using GPT-4 Vision itself, there's a tutorial I've linked in the notebook, but essentially there's a lot you can do with this thing. So the basic way that you use it is, if you're familiar with the chat completions API, essentially the way it works is you pass it some text, your prompt, and I say, hey, what's in this image? And there's a kind of a new type of prompt. It's called image URL. And this image URL is basically a direct link to your image. In this case, I just used the default from the tutorial. It's a picture of this boardwalk. The real power of GPT-4V is that you can kind of use the same kind of prompt engineering techniques you did with just plain text, combine it with images as well. So in this case, it generates a really good caption. It's pretty accurate. Wooden boardwalk pathway with the green grassy fields, blue skies. That's great. So what that means is that it's really good at understanding the image. I also want to upload my own images. So in my case, I've got a bunch of local images and I have a big problem. The names for these images are not very good. I would like the names of these images to actually reflect what the contents of the images are. So what I need to do is I need to actually base64 encode these images. And I'm using what's called the data URL syntax. The same technique you use in any web page. Essentially, it's a way to kind of include an image inside a much smaller string. The downside is that base64 encoding makes these images a bit larger. You can expect about a 1.3 times size increase because the binary encoding of an image is a lot more efficient. But the upside is we can represent it as a string, and we need to pass strings through in order to use a local image. So in my case, I have a prompt, generate a file name for the image, only include the file name and nothing else. So when I run it on picture 33, which is the mountain of the sunset, I get a much better file name, sunsetmountains.jpg. So you can imagine, like, I can basically take the output of this completion and I can basically loop through and rename all these files based on what GPT-4 Vision actually thinks they should be called. That's like a really, that's just like an easy example of what you could do. As you can see, it can generate captions. You can ask it analytical questions about images, like in this sample where I basically say, compare the impact of interest rates and GDP. It can answer more complicated questions. It can do things like reading charts, reading graphs. Again, we don't exactly know what the training set of the GPT-4 Vision model is, but we do know it's seen a lot of things because it can answer really complicated questions. Like I said, financial documents, but as Pamela said, like there's limitations. We specifically called out medical diagnosis as something you shouldn't use this model for. So I wanted to pause here and see if there were any questions about anything we've talked about so far.
Let me see. The main question was, can we do a search with images, right? Because I think you showed search with text in your app. Can you do a search with images? I don't know if you had a demo specifically showing that one.
Yeah. So I don't have a demo for you specifically. So there's unfortunately a limitation of custom vectorizers today is that they only accept text. I think in the future they will accept images, but for now you will have to kind of manually call the embedding. So what you can basically do is you can go to the function app code and you can kind of just copy paste the code that calls vectorize image, and you take this output vector, and when you actually search, let me see here, when you actually search the image, what you can do is I can go into the JSON view. Basically, when I pass the vector queries, I pass the actual vector as an array, and then so in my case, I think an easy way of doing this. Let me see here.
You can copy paste the vector.
Yeah.
So fun.
Let me see here. So I used the API wrong. The kind is vector. Yeah. So I literally just copy paste a vector in here. And this, the key insight here is that the embeddings that come out from the vectorized image and the vectorized text API, you can compare them. So because you can do that, you just basically swap out the vector you're passing. You can't use there's no image kind. You'll have to do this yourself. That's the only kind of caveat.
Yeah, but that's totally doable. The vectorizer is really just like icing on the cake. Like that just came out really recently. In my day, 2 weeks ago, we would just compute the embedding ourselves. And that's what we do that in our RAG chat repo right now. So yeah, that's really helpful. Kevin was asking, how important is it to give descriptive names for the images? I'm assuming that's part of maybe that's part of the GPT-4 vision call. What does that GPT-4 vision call look like?
So that's a great question. So if we look at that notebook that I have, so the GPT-4 vision call is literally just a blank link to an image. So you'll notice in the URL case, like, the name of the image is in the URL, but in this local case, there's no description of the image at all. I just purely pass the image base64 encoded to GPT-4, and it actually opens the image, and just like the same way Clip could take the image with no description at all and just say, hey, a photo of a mountain is a better description than a photo of a beach. GPT-4 Vision does exactly the same thing. And purely by just asking it, hey, generate a file name, it says Sunset Mountains. So it doesn't need any description at all.
Right.
If you wanted to do a specific task, you would definitely include that background in the prompt. Like, for example, in our prompt, the formatting completed, we tell it, hey, you're an intelligent assistant. The documents contain this. So that prompt engineering comes in when you want it to do a specific task with the image, but you don't need to describe the image itself. And that's what makes this so powerful. You can actually go the other way around and generate descriptions from GPT-4 Vision, like I am doing in this case.
Yeah, so you can just pass it the image, and this is just a specific example of using a prompt that generates a file name, because we had a question like, oh, can the file naming be used for citations? If you're trying to get citations, you need to do that wild hack where you actually write the citations into the image, because the problem is if you give it that image, it has no idea what the file name is, right? For a citation, we need like an actual permanent identifier that is the same in our blob storage and is the same in the GPT response. So for that, if you're trying to get citations, because imagine you're passing it 5 images, you want to know which of those images did you get the answer from, right? So when you're trying to do this sort of thing, where we're trying to do a RAG on images, then we have to put that file name inside the image itself, so that then the LLM can respond and say, I found this information from here, which is, so it's just different from the other use case.
And that actually, the instructions to do that have to come in the prompt. Like what we do is we actually draw the name of the blob on the image. Then we have to go in the prompt. By the way, the source name of the image is in the top left corner. So you can imagine if you didn't want to display this, you'd have to kind of have two copies of the image, the original one and then one with citations. So it's kind of an interesting hack, as Pamela mentioned, to get citations to work. You have to actually write it on the image, kind of in the margins almost.
Yeah. So Isaac says, hopefully OpenAI updates vision to fix needing that hack. How would they, is there actually updates planned? How would you improve that situation?
So this is purely speculation. If I were them, I would have a like extra field here, like identifier or something. And it's like, I would prefer that, but that doesn't actually exist.
Okay, that's true. That would make sense. That would be much easier than all this code we have right now to write file names into there. That's a great comment. Okay, those are the questions for now.
Awesome. Yeah. So I guess just wrapping up. So deploying this thing, I think the unfortunate part about this is I don't believe there's a low cost option for GPT-4 Turbo with Vision. You can deploy on the actual OpenAI account, but Azure OpenAI, Pamela, correct me if I'm wrong, but I don't think there's a low cost option for that.
Right, because we've been encouraging the low cost free deployment for folks working on the hackathon. I haven't even attempted trying to get that to work with GPT-4 Turbo with Vision. Because let's see, right, we need the model, which maybe you can get that off openai.com. So you could try to make it work. I think you'll have to do some work, but the Azure computer vision model, I don't know if even that has a free tier. So probably, I'm guessing it probably doesn't. So I think you would at least have to pay for Azure computer vision, and you'd have to pay someone for the vision model.
Yeah, the alternative is to run a model like Clip locally, and there's some code here to do that. The choice of model here is important. I'm not sure Clip's the best one anymore, so some experimentation might be needed, but we just have some sample code here on how to get embeddings out of Clip. And the same way we're comparing embeddings out of cognitive services, you can do this, you can just swap it out for this, and that eliminates your cost. The downside is the cognitive services embeddings are more generic, and they might be more what's the word? More oriented towards your use case. So choice of model matters a lot here because the results you get, a lot of it has to do with the training data. GPT-4 Vision is very like kind of jack of all trades. And this is kind of like the most intelligent, like, hey, given an input, like I can run prompts on it. But in order to find the relevant images, I need to embed them and do search over them. And typically the way we do that is we create an index in Azure AI Search, we upload the vectors, and then we let it do this cosine similarity search for us. And that's kind of like the RAG loop that Pamela was talking about. So yeah, I mean, if there are no more questions, that's pretty much all the content I had for today.
Okay, then I have bonus questions.
Sure.
So you mentioned it's really slow, right? The implementation in our repo. So maybe we could talk about why, what aspect of it is slow, and then ideas we have for improving the speed up, and maybe someone would like to send a pull request who's watching.
Yeah. So it's actually super interesting. So this is not using our sample at all. This is purely using, what's the word? It's purely using just the GPT-4 model itself. And I need to rerun some cells. So, oops. Yeah.
Just rerun
this
all
is
the
how
cells.
Jupyter Notebooks is. If you lose your contacts, you have to rerun all the cells. So what happens when I run this is the problem that we are facing. There's two problems, right? So, and of course, there's no access to this. Okay, so I can't run this, but basically, if I were to run this, it would take about 30 seconds. And if I run this, and I can kind of show you guys, you'll just see it's generating your answer. I can actually see what it's doing in the console output. So the problem is that it's spending a very long time actually getting the completion itself. When I've measured it, I know getting the completion itself takes about 30, 40 seconds. So yes, there might be optimizations we can make in the actual sample code itself, but there's a core problem of the GPT-4 turbo responses come in very slow. And that's kind of the bottleneck of the whole thing right now is just that we're getting slow responses. I imagine over time, as it comes out of preview, it'll run faster, but for now, you can expect run times of like over 30 seconds, possibly even like more than a minute. And it just depends on how many images you pass it. Empirically, I found running this sample with images available on the internet is faster, but I can't confirm that. I do know that if you upload images locally, it might be slower. It might not be. It's hard for me to say. I haven't extensively tested it. But when it comes to optimization, it's very difficult just because the completions come in slow.
Okay. Yeah, that was the thing I was thinking about where Shakir thought that maybe if we used URLs instead of data URIs, like, doing signed blob URLs, that maybe there'd be a performance improvement. But we haven't scientifically, run the numbers for that. But that's something to keep in mind. But so maybe they do say all over that this is in preview mode right now. So you shouldn't be using this in production. You probably wouldn't want to use this in production because you'd get a lot of complaining users about how slow it is. But there might be some use cases, like maybe this isn't actually quite ready for a user-facing chat application due to the speed. But as you saw, like there's lots of really compelling use cases for image multimodal embeddings and the sort of stuff you can do once you've got these image embeddings.
You can imagine, like, to give an example, like let's say you have a large amount of images for a website that's not accessible at all. You can literally download all those images, run them through GPT-4 Vision, and generate a caption for every single image, and just upload it automatically. So you can imagine, like, I have a folder of pictures. I loop through this entire folder, and I rename all the files. I add metadata saying, "Oh, here's the nice caption." So you can imagine you could kind of like make it a website that's not accessible at all, totally accessible with hovering tips. And that's really why this is so powerful. The lack of kind of interactive responses, though, it definitely does limit what you can use it for. I agree.
Yeah, it's really exciting though. And apparently Kevin looked it up that Azure AI Vision does have a free tier, 5,000 transactions per month. And same with the image analysis multimodal embeddings API. So that's really nice, something for people to explore if they can use that free tier.
Mm-hmm.
All right, so I just asked to see if there are any other questions. I don't know if anyone's frantically typing them, but if you do have additional questions, please post either in our AI chat app hack forum, or also if you're trying out the repo and actually trying to do the RAG with images and you run into things there, you can also file an issue there. Basically, everything goes to my inbox. And also Matt is also very big in the issue tracker. So we try to be very, very responsive and try and improve these tools for all of you to be able to use, and also try to figure out like what are these common use cases, right? Like, is everybody trying to do a particular thing with image embeddings and multimodal embeddings? Then how can we make that easier for everyone, right? And so that we can develop more easy to use repositories to fork. Okay, so let's go ahead and just switch back to next steps. There we go. Thank you. So so thank you everyone for watching, and thank you so much, Matt, for all those really, really cool demos that got us all really excited. There's so much stuff I want to do right now. I just say, when I was a kid, the way I spent my weekends was I would go to my dad's office. He was a computer science professor at Syracuse University. I would go to the office. I would sit there. I would caption family photos all day long because we were very early on like the camera photo digitization, and he wanted them all to be captioned because he was developing a photo system in Java at the time. And so I would spend my weekends captioning photos. And if I had this, I could have maybe had a life. Probably not, but so we actually still have those photos because he finally moved it off the Java server. So I do actually want to try and run these on those photos. So just an example of something that really excites me about it. So next steps, if you are not registered yet for the hackathon and you are interested on hacking on a AI chat app, please do register for the hackathon at that URL. And then you can start deploying our RAG repo. And a lot of people, will want to start by deploying for free to minimize costs. So you can go to that aka.ms/ragchat/free to deploy for free and from a free account. Post in the forums when you have issues or questions. I'm trying to answer as many as I can, as fast as I can. And join us next week. So next week, we're going to have a bunch more sessions covering lots more topics. We're going to have Matt back. Matt is going to be talking about access control and authentication for RAG apps, which is a big feature that he has added to our app and is something that search customers are always looking for. So he'll be talking about that. We'll also have folks from actually from the JavaScript version of the repo. We'll have Anthony talking about function calling. We'll have Chris talking about evaluation and prompt refinement. So we're going to have a bunch of cool sessions. We're going to have some MVPs. So please do join for next week's session. And then when you are done with your hack, make sure to submit it. You can see the instructions in the repo. So thank you, everyone, for joining. This was a really fun session. Thank you, Matt.
Thanks, folks. Bye.